First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts.
I think Roy's kind of a noob on today's episode.
Maybe. It kind of depends where it goes. So
tables have turned, sir.
I'm not a noob. I'm just less of an expert.
Less of an expert.
So, Eddie,
just
what
like
are
most
we?
of the time, you're less of an expert than me.
Oh,
never.
Burnses. It Burnses. So,
You haven't even admitted.
what? Say again?
I used to be able to admit it, but we're at like episode 41, and
Are we?
Yeah.
Oh, wow.
when it comes to spin itself, I think I'm pretty good at it at this point.
Have you been learning from these episodes?
Little tiny things here and there, yeah, but
mostly you're already on top of it.
mostly it's just like I know how to do it in other languages already, and I just hadn't done it yet in spin. But by having to explain to you how these things work under the hood, now I know exactly how they all function for this platform too. So.
Got it.
That sort of applies for me also. I mean, some of the things I didn't really know the spin specifics.
Yeah.
But I knew the concepts just from programming for 30 plus years. So
Gotcha. So
the other thing is learning some of the weird things that spin can do that a lot of other things can't do.
Oh, interesting.
Yep.
Interesting. So I first wanted to let you guys know, to our listeners, so I usually come up with the topics, and ever since getting through all the modules and the sensors, I'm kind of at a loss for like the next few, I don't know, episodes we are doing.
Like the rest of them from now until we decide to stop years from now.
Right. So I have a forum post thing going up in the Parallax forums that is looking for ideas. I know some folks have already put some ideas up. And I pretty much need you guys to put ideas. Otherwise...
Yeah. The main thing to keep in mind,
I don't know what to ask these guys.
They need to be things that can be done in spin or are generally done in spin, maybe with a little bit of helper from some other module.
Mm-hmm.
Some of the examples people have been putting up have been like
PASM only,
PASM specific details and stuff like that you can't really do. Like one of them mentioned doing the video generator, and you really can't do the video generator from spin. You have to use a PASM object, and then spin can talk to that to draw.
Well, so you can use spin code though to interface with a PASM object.
Yeah.
Right, yeah. But I'm just
as long
saying
as
that
we stay in that realm, I think it's fine for Addy to be doing that sort of thing.
But trying to explain to you the video generation circuitry on the propeller and how to use it in PASM isn't going to be a good first spin topic. But how to use, TV text dot spin, which is an object that has some PASM in it, then that, could do that.
All right, so we can do that. Okay, so for those who are interested, feel free, please, to put your ideas there. Otherwise, if I don't have an idea, then we don't have a episode, a show.
Yeah, we'll wing it.
Yeah,
kind of like today.
Right. So, kind of. So today's topic actually comes from a project that Whisker's been working on. It's a proto-synth, which if you haven't seen the video, please go watch the video now. But
link in the description, I'm guessing.
Right. And I think yesterday or 2 days ago, he was mentioning that the prop could generate sine waves and sawtooth waves. I don't know, just different kind of waves, sound waves. And I was like, oh, I don't know if I knew that.
To be accurate, it's emitting approximations of them.
Right. Well, that's fine. For our intents and purposes.
The only thing it can actually output is square waves directly.
Oh.
But if you use tables of data, you can do other shapes, but there will still be approximations because of discrete locations.
We'll have to get into the details of how that works, Roy, but let's let her finish her thought here.
Oh,
sorry.
That's fine. Anyway, so I thought it was interesting because I didn't even really know that the prop could generate sound waves. I don't even really know how that works, but yeah. So I thought that it would be a good idea if we discussed sound today.
Cool.
Well, one thing, just as a sort of basic electronics / sound / wave thing, is that generating electric waves or sound when that electric wave is applied to a speaker is, a lot of electronics can do it. Any microcontroller can. The prop certainly can. Is just how well it can do it is where you run into issues with certain controllers.
And what's the limiting factor? Is it clock speed? Is it RAM?
Well, clock speed.
We should probably give the fundamentals here first so that she knows why those things are important. Okay, so I'll just cover it from the basics here. Okay, the prop doesn't have an analog out pin, right? It doesn't know how to do like
it just does
a voltage, right?
1 or zeros.
Right, so it's either on or it's off.
Right.
Okay, and you've used a low pass filter before, right?
Sure.
It's basically there's a capacitor and a resistor there, a little RC filter.
Yeah.
It lets slower things through.
Yeah.
And faster things don't get through.
Right.
So the idea here is that if you turn on a pin on and off really, really, really fast, you're essentially charging up that capacitor.
Yeah.
But the on and offs themselves won't make it through the resistor.
Sure.
Because the capacitor is sitting there trying to discharge through the resistor constantly. So the offs never get through unless there's a lot of offs in a row. So by using this trickery of how many offs versus how many ons, you get an average out the other side of a low pass filter. So that's the basic version. Now you apply pulse width modulation to it. Now you're changing how long it's on versus how long it's off. And again, you can create an average on the other side of your low pass filter to create a voltage between 0 and what's the max the prop can put out? 3.3 volts. So you can create a voltage somewhere in between those two. And then if you change that voltage over time, you can trace out waveforms on the timeline.
Right.
So like if you stick a scope to it,
you would see it going up, down, up, down, up, down. Now, if you trace that wave at a fast enough frequency, it becomes audible. Human hearing range. Audio signals, right?
Right.
And then if you do it at a specific frequency that we recognize as like a middle C, suddenly you have a waveform that's oscillating at a musical tone.
Right.
Okay.
So one thing just that I needed explaining to me way back in the past that is helpful to understand in a little more discrete terms is the outputting to the filter. You set up the resistor and capacitor values based on your voltage so that you get what you want out of it based on the size of the pulses that you're outputting. So you have to tune the capacitor and resistor to the appropriate values that you want. And then when you output your on-offs, right, if you output equal time on, equal time off quickly enough, you'll get half the voltage instead of full voltage. And if you output a quarter time on and a quarter time off, you'll get a quarter of the voltage and, whatever ratios. But you don't just automatically get that with any capacitor and resistor. You have to pick the appropriate capacitor and resistor values to get the output voltage range and swing that you want. And there's calculators on the web.
It's actually a very simple formula.
It is a very simple formula.
It's very simple algebraic formula for calculating out any capacitance, any resistance, and what frequencies are going to go through. And this. So
then, would you need
this is one step removed what Roy's talking about.
So is this code driven? Because, say you get one resistor and one capacitor, that's perfect for the vocal range, or middle C or whatever, right?
Well, no, it's more about what voltage output you want, what voltage range you want, not what frequency.
So say I want it from 0 to 3.3.
Right. You would need to pick the appropriate.
Remember, we're talking about a low pass filter, but the low pass filter isn't blocking out frequencies in the audio range. it's blocking out the frequencies of the on and offs on your actual pulse width modulation, so that those don't ever get past the low pass filter. You don't have any, what would we call it in a power supply, Addy? Do you remember? When you're designing a power supply from an AC to a regulated DC.
Rectification?
After rectification, you have a slight problem that you have to correct with smoothing capacitors.
Oh, that funky wave thing.
Yeah, what's it called?
Chunking. I don't know.
It's called a ripple, right?
Right.
Ripple.
Now, when you look at this digital
ka-chunk.
pulse width modulated audio signal, if you were to zoom up in very close on each one of those big audio waves, you would see that they were actually on, off inside of them.
Mm-hmm.
Tens of thousands of on and offs for every single one, right?
Mm-hmm.
Right.
And that's our digital jitter, and we want to get rid of that.
Yeah.
So we completely remove that by blocking out frequencies above whatever. But like Roy was saying, you want to design your filter to stop those, but you also want to design it so that the values that you use allow you to very easily know where halfway is. Because your waveform, like a sine wave, you want to know where halfway up it is.
Mm-hmm.
And it's a lot easier to know that 50% duty cycle is going to give you a voltage that's exactly halfway up your range.
Okay.
And that 100% duty cycle is going to give you peak.
Okay.
And that 0 is going to give you 0. But that, 25% is going to give you, 1/4 up.
Okay.
Because then it's easier to write your code to hit the exact spots on the voltages that you want.
Right. Right. And the other thing is just that the output can be tuned to give you an appropriate range of voltages for a given type of audio signal, potentially. Although sometimes you'll run that through some other circuit to feed it into an amplifier.
Okay.
But those are details that are more in the electronics land, not in programming land.
Right. So I'm still a little confused as to where the code comes in.
So the code is turning on and off the pin at some rate.
Some crazy rate.
So like the simplest version is you could just have a little loop that turns the pin on for some amount of time and then turns it off for some amount of time and just goes forever, right? That's the simplest version of this. And you would just get a fixed voltage out the other side.
Yeah. And it helps if you think about it. If you stop,
that'd be a square wave, right?
If you stop trying to think about it in terms of audio frequencies and just think of it in terms of like a low frequency oscillator that's going up and down slowly, your code is turning it on and off at a certain speed here at the beginning of the wave, and it's more often on as it goes up the wave more and more and more often. And when it gets to the top, it's on all the time, and then it's less on and less on as it swoops back down the sine wave.
Right. So just to correct you a second ago, you're saying that would be a square wave. Well, yeah, the pin would be outputting a square wave, but the filter is going to turn that into a voltage, just a straight DC voltage.
Averaging out the amount of time.
Because it's charging a capacitor and with that smoothing
is discharging through the resistor, and that discharging through the resistor is your output.
Right. And then in order to get that voltage that's on the output to go up and down, you have to change the size of your pulses that your code is creating.
Okay.
So you make it longer in the on and less in the off, and then you'll get a higher voltage. And if you make it less in the on and more in the off, you get a lower voltage.
Okay.
Right. And so you just keep outputting this square wave on the pin that turns into a voltage, and you change the pulse width size to get more or less voltage out of the output. And so if you're constantly changing the pulse width size, that's called pulse width modulation, because you're modulating the size of the pulse up and down, whatever values you want, to produce an output voltage. And you could do a simple version which produces a square wave signal on the output by just going, between all the way on all the time and all the way off all the time on the pin at a slow frequency, right? But what you really want to do is create a wave shape like a sine wave or a sawtooth or a triangle wave or other interesting instrument sound timbres and
square
whatnot.
wave is a very useful one to do, actually. And I know it's a little bit weird to think of that you're building a square wave out of a bunch of pulse width modulated square waves, but it's a very useful one because it has tons of harmonic content. So
right, and you can intermix. You could have a really complicated program that is taking one square wave and another square wave and blending them on top of each other by changing the pulse width in between two different values really fast.
Now, and
then both of those are swinging up and down appropriately.
So you could have like all 8 cogs doing different types of.
Well, like as an example, the SID cog that you've heard can do 3 different voices, so it can produce 3 different sounds.
It does that in one cog, and it's mixing the waves together in software by averaging out the 3 of them. What voltage level they would be at, Eddie. It takes all 3 of them, averages them together for that moment in time, and then actually does the pulse width out for the average.
So how do you get the prop to read the voltage, like what voltage that particular pin would be?
Well, the prop doesn't read it. The prop sets it. The prop is doing you're turning the pin off and on, remember?
Right.
Using code.
Right.
You're turning the pin off and on, and that's causing a particular voltage to come out the other side of the filter.
Right.
And so if you turn it off and on quickly enough and then change how often you turn it off and on and how, the size of the on period versus the off period, if you change that over time, you get a shape of the voltage coming out. The voltage coming out of the other side of the filter will go up and down and create a wave.
So depending on, sorry, I know this is like, it feels like it's rehashing the same thing, but so how fast you turn on and off the pin determines the voltage.
Okay, so about the speed thing, the speed is typically constant.
Yes.
It's typically, it's on bam, 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 bam. That's always the same. How we're controlling the voltage is how long for each of those cycles, if we will, it's on versus how long it's off. And that's our pulse width.
Right. So if you have it on for 50% of the time and off for 50% of the time, then you're going to get half the signal.
I see.
But if you have it on for 90% of the time and off for 10% of the time, then you're going to get really tall, high, close to 3.2 or something, right? Really high value.
And that's a result of you're charging the capacitor for a longer period of time before taking its power away.
Right.
So you're both pulse width modulating and frequency modulating.
No.
Yeah, because the frequency determines
the
type of wave.
You're affecting a frequency output. It's not frequency modulation because that's different. That's like, FM radio is frequency modulation, and that's a really complicated thing that we don't want to go into right now. But you're causing a frequency to come out the output by doing pulse width modulation.
So if you want to think of it in ham radio terms, your carrier wave is the pulse width frequency, and you're doing frequency modulation of the audio, frequency that you're encoding into that. But, it's very different than what you're doing in ham radio, and you really shouldn't sort of put your head in that state because you're probably going to run into some walls there that I'm not familiar enough with ham and radio frequency stuff to know about. So I'm not going to try to explain it through that metaphor.
All right, so it's through the magic of pulse width modulation.
Well, it charges up the capacitor. The capacitor discharges. It's not super complicated.
And you get a voltage, and as the voltage varies on the line, that's a wave. Right?
So
all the wave is a changing electric signal, right?
You were asking about how it actually makes an analog voltage there, because you can't do that with just a basic output of the prop. This is how you can create an analog voltage that you have very accurate control of with just a single pin off the propeller. And then you asked, where's the software come in? The software comes in by dictating the shape of that voltage over time.
Right.
And that's where you're tracing out specific frequencies that you can use to achieve various tasks, be it, generating some analog signal to test some equipment or making audio frequencies or whatever you want to do.
Okay.
You don't sound convinced.
I think I'll have to draw it out or something in order
that could definitely help. But you just need you kind of got to separate in your mind the fact that you're outputting a square wave that is at a constant frequency, but you're varying how much it's on versus off. That's what your software is outputting.
So it's a constant frequency.
Right.
Because it's a constant hertz.
You're turning it on and then turning it off and then turning it back on. That cycle is constant time. But how long it stays on versus how long it turns off in that time slice determines the voltage that you output. So when you vary it up and down in amount of time on versus off, you can change the output voltage up and down because of the filter, because of the capacitor resistor filter that's on there.
All right, wait.
I can explain this very easily to you with the water analogy if you want me to, because that always seems to click in people's heads. So you got a big bucket, right?
Yeah.
And there's a small drain at the bottom of the bucket.
Yeah.
That small drain is the resistor, the output of our filter.
Okay.
And the bucket is the big capacitor, right? And then up at the top of the bucket, you've got a hose.
Yeah.
And you know that every 1 second, that hose is going through its cycle.
Uh-huh.
And the width of the pulse on that is how long for the first part of the cycle that you're going to have that hose on versus off, and that's a ratio. It's a percentage. 0% means for that cycle it's not going to come on at all. 100% means that it's going to be on the entire time during that cycle. Okay? So therefore, the wider the pulse width going on right now, the more water is going to be filling the bucket, the longer it's going to take for that water to flow out through that resistor.
Wait, say that step one more time. I feel like I was okay. Say that last step one more time.
Which part?
Crap. I got the hose and the cycle. Okay, so if it's 0, then it's the nozzle's closed. If it's 100%, then the nozzle's open the entire time.
You have to think over time here, right?
Yeah.
Okay, so you gotta keep that fourth dimension going, that over time.
Okay, now and then the next part.
So the longer it's on, the faster that bucket is filling.
Right.
The more it's full,
the
longer it's going to be before it's empty.
Yeah.
Because the flow rate, the flow coming out of that resistor is, changing, right? How much over time, because, we can't use the water analogy exactly.
Okay.
It does break down at a certain point, but, I'm giving you that charging and emptying.
Wait, can I let me just ask, maybe they'll just clarify everything. Okay. So the voltage coming out.
A better spot to maybe look at is how much water's in the bucket at any given time. It's your potential, right?
Okay, but give me 2 seconds. Okay, so when a pin is on, it puts out 3.3 volts. No questions asked. Pin is on, off, it puts out 0 volts.
I'd rather you get this before you move on.
I think I get it, but
So with the pulse width, you have a constant drain of voltage out of the bucket.
What?
Hey, with the pulse width, you have it constantly filling up according to how much pulse width you have, and at the bottom you have a resistor constantly draining it.
Yes.
You're fighting against that resistor with the width of the pulse to set how high you currently want to hold the level of voltage in the bucket.
Okay.
And that's your output. And then over time, you're changing that up and down, but over time, you're tracing out a sine wave on the fourth dimension there.
Okay. So, I think I kind of get it. But let me just see. Let me see if this also helps to explain it. So, your pin is doing on, off, right? And your pulse width is determining how long it's on and how long it's off, right?
Right.
That, if you measured the voltage right at that pin, When it's on, it's 3.3 volts. When it's off, it's 0 volts, right? But if you were to measure the voltage at the end of that filter, it would change.
Yes.
Depending on how long it was on off, because how long it was on off changes how much voltage essentially the capacitor holds, right?
Mm-hmm.
And so you'll see that resultant effect after that resistor.
Mm-hmm.
Is that it?
Yep.
Yes.
All right. I got it now.
All right, so that's the
25 minutes later.
That's like the how, right? And then the software is changing that over time.
Yeah.
At a very specific frequency. And then of course you're getting into, you have to think about how are you storing your wave, right? The information that describes the different points in your wave are along several slices.
Mm-hmm.
So you have a certain frequency of pulse width. And that's where your slices are going to happen on, your waveform. So if you're doing like a triangle wave, and you know that you want your triangle wave to be, a frequency of whatever, where your lowest point's going to be, where your middle point's going to be, where the top point's going to be, where the middle point's going to be, where the bottom point's going to be in time.
Mm-hmm.
Right?
Mm-hmm.
And you can use a little formula to figure out any point, height-wise along those lines of a triangle wave, very, very simply.
Okay.
And then you're picking your frequency of what you want it to sound like, right? Say 440 hertz, an A. Okay. So you know that you want those peaks, peak to peak, to happen 440 times a second.
Okay.
All right. And your pulse width is X fast. So you have to find that, that harmonic of I need to ride up and down this wave 440 times a second, but I can only represent it on my output for each slice of that pulse width modulation clock. And that's your sample rate.
Okay.
Yeah, I'm sure you've heard the word sample rate before, right?
Yeah.
Okay, so that's like each representation, each time we actually set the level of that capacitor is one sample.
Right.
I guess
one cycle of setting the pin on and then setting the pin off, right? How long you set it on and how long you set it off, that's one cycle.
Right.
And that's one sample of output.
Right.
And you can do that for each of your, your pulse width periods, you're setting your voltage to a different point, right? So it's only when you have an opportunity to set that voltage to a new point that you can actually represent a sample. So in your code, you may have a vast resolution of your sample because you're dealing with an algorithmic representation of a triangle wave. You can sample that sucker wherever you want with some accuracy, but you can only output a voltage to represent that part of where you're at in the wave at the moment, according to 440, each time you have an opportunity to set the voltage of your output.
Right. And one nice thing with the propeller is that you can set that very high.
Yeah, very, very, very high because it runs at 80 megahertz.
Right.
Well, and you also have, with the clock counters, you can actually go above 80 megahertz.
Oh,
for your with some weirdnesses.
Right.
But they can do some interesting, super high frequency stuff that is outside of audio range using
So go back and listen to Pulse Width Modulation. We've covered that, and go back and listen
someone
to
said
counters.
That servos were not real Pulse Width Modulation.
No, they're different. They're kind of like it, but not exactly. And listen to
everybody wants to mess with my mind today.
Listen to the counters episode that we did. And between those two things, the pulse width and the counters, use the counters to do the pulse width at a really high frequency, and look up that, maybe Addie will find it, put it in the description, the formula for calculating out a low pass filter. And honestly, at these speeds,
we might end up having to go through it next week.
The audio filters the audio equipment that you're plugging it into doesn't function at the speed of the pulse widthing. So yeah, you're probably not going to hear it anyway.
I have a question, Whisker.
We don't have time.
No, I do. Do you have code for the sawtooth, square wave, and all that. Those types of the basic waves.
There's a new module that was featured in an object a couple of weeks ago as the object of the week.
Okay.
Called the Propeller Signal Generator or Propeller something along those lines.
Okay.
Isn't it done by the same guy that did SidCog?
Yeah, Johannes A8. I can't say his name, but he's one of my favorite developers for the prop.
Okay.
I use all this stuff.
Okay. So it's in there?
Yeah, you can.
All right, I'll look at it. I'll see if I can tease out the bits.
We could also make a simple program to possibly do it for you.
Okay.
I could work with you on that.
Cool.
I've been doing that all week, so I can just hand her what I've got. I made a little sequencer that does it one frequency, then another frequency, then another frequency over time, so you can just turn some dials and go boop, boop, doop, 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 boop.
Okay.
Okay. Well, that's actually all the time we have for this week. You guys can find this show every Tuesday evening.
Yep.
On firstspin.tv. There's an RSS feed there. You can subscribe to the show on your phone, iTunes, anything you like.
Yes.
And until then, we'll be back.
See ya.
Bye.
Later.